Actually, what I want to do is, go to the following a little bit, because, we're talking about 1900, and one thing I'll do is just read you some of these quotes that why Lynn has chosen 1900. And there's sort of two critical events, one in particular, which is Hilbert's umpteen questions. Sort of being Jewish, I think, it's sort of like the Passover, why is tonight different than any other night? 4 questions. He's got 20 some odd questions. There's some dispute over these questions because some of them he put in the original package and some of them he put in later or before. He didn't read them all. But this was read for purposes of people knowing some historical facts that are relevant. These are remarks delivered by Hilbert to the Second International Congress of Mathematicians in 1900. Oh, it doesn't give the date. I thought it gave the date. But anyway, and this is in 1900. So, and he basically sets what is meant to be the standard, not just for mathematics, but for science, as you'll see, to clear up all of the vagaries, the lack of rigor. As I told you the other day, there was all this dispute about Riemann and the Dirichlet's principle. It wasn't rigorously proven, so you have to clean up Riemann by establishing some rigorous formal standard. Now they deduct, and you'll see he's very clear on this. He actually says it's got to be deductive. Okay, now at the same time, you have 1900 is the year that Planck discovers, or puts out the quantum. Okay, and so, at this point, and soon afterwards, 1905, you have Einstein's so-called miracle year. And maybe there is something to some people have suggested this. I mean, it is true this is a year where Einstein puts out a whole series of important papers, on the photoelectric effect, on special or electrodynamics of moving objects, which became special relativity, and so on. Now, on the other hand, there are those who want to argue that this was more important than anything Einstein did. And it's a way of leaving out general relativity theory or throwing more questions on, how much is general relativity to be completely accepted. At any rate, it certainly was an impressive year. So, in 1900, Hilbert sets this standard, which I'll give you some examples of. And then you have Einstein. Now, the other thing to keep in mind during this period, particularly for us, and then I'll take a step backward, is this is also, roughly speaking, I think Pierre Curie dies in like 1905, 1906. Yeah, I knew he's in this accident or non-accident. We're not going to discuss that at the moment. But the point is that Pasteur and Curie are working on this question of what is the characteristic of life? Okay. What is the principle which clearly distinguishes life from non-life? I mean, there's more peculiarity. I mean, think about what a funny thing this is in its own way. 1 minute something is alive. Now maybe you can say to yourself, well, if something gets smashed, it's obvious why something is crushed, so it's no longer living. The mechanism is broken. But what happens in the case of something that merely dies of old age or some disease, and particularly of old age? What is it that defines the difference between that, whatever, animal, human being alive and being not alive? This actually has some serious consequences. For example, there has always been a question, Ernie may know the latest, I don't know what the latest is. Are viruses really alive? That's bacteria, it's a given they're alive. They have a certain internal motion, etc., etc. Viruses are a real funny question. because there are certain things that they are incapable of, and there are certain things that they're capable of. It's not clear whether they're really abiotic or biotic. And with the human being, to get a little, you can say, I mean, you've been in the room when somebody passes away. It's not always, even that is a difficult question. Because sometimes the person may or may not actually be alive. It's not an easy thing to determine when it's dead. There's, of course, when you go back a little bit into the 19th century and earlier, you find cases where people were thought to have been dead, and they weren't, and they were buried. Because every sign was that they were gone. Now, of course, we have measurements, but even today, I mean, take the question of, that comes up in all these euthanasia discussions. At what point are you dealing with a cognitive being? At what point are you not dealing with a cognitive being, or a human being, or what potentials are there? Now, even more, in a sense, more importantly, what happens in life? If we're going to deal with life, if we're going to deal with medicine, healthcare, what is it that characterizes life? And with life, you say healthy. Now, it's a funny thing. You would never say about a rock it was healthy or not. It's just a rock. That's all there is to it. Now, when it comes to life, you say, well, it's healthy or it's not healthy. Presumably, some idea of whether it's headed downhill on its way to being non-life, or it's in the flourishing of its life capabilities. Now, one of the things that people like Pasteur and Curie were looking at is, of course, something that becomes very important to Vernadsky, which is there some characteristic of space-time which gives us an insight into the distinction of life? Now remember, so all this is occurring around the same time, in the broadest sense, and actually not too much difference in time. Planck was working on the quantum problem for a while, the black box radiation and so on and so forth. This wasn't something that just sprung overnight. This was an issue for the last couple of decades of the 19th century. And by the way, these seems like odd questions. The radiation in a black box, it's a pinhole, and I always get the story a little bit screwed up. But anyway, what's the interest in this? Well, I'll tell you what one of the things was. That one of the things they were working on is light. And they were trying to find some of the most effective ways to have light bulbs and what kind of material was required to make light bulbs work better. This was being heavily worked on by Siemens. Einstein's father was involved in some of this. He was an electrochemist. The family was involved. His uncle was an engineer of some sort or other. Okay? So, these things were being intensively looked into. And Planck does, the point is, Planck, at least himself, is not 100% happy with the conclusion he comes up with. Because he says, well, this requires a certain quantization of something that we've normally handled as continuous. Electromagnetic radiation. Normally we handle this as though you can have any value between 2 points. You don't have to think so much of frequencies, wavelengths. You can have any value, any frequency, and therefore you can handle these things from the standpoint of infinite division and so on and so forth. What Planck finds out is the solution to the problem is that that's not true. That indeed electromagnetic phenomena, radiation of various forms, comes in packages. It's quantized. That's even more important, I think. As I said to you the other day, in a sense, Kepler's orbits are quantized. At one level, this is not as strange as people thought it was, but they were thinking from the standpoint of waves versus particles. Okay, so therefore you were either a wave or a particle. And waves should not show quantized effects. They shouldn't become in only certain packages, and as it turns out, they do, which is the famous Planck equation, Planck, h times the frequency. Okay, and h is the so-called Planck constant, and whatever the frequency is. So the energy comes in those frequencies. In other words, if you're dealing with a certain event, and you have a wavelength of a certain frequency, it will jump in energy multiplied by h, which is something like 6 times 10 to the minus 23. It's not a big number. Okay? But it does come in those kinds of clumps. And when you're dealing with subatomic phenomena, 10 to the minus 23rd is not insignificant. You're dealing generally with extremely small phenomena. So Planck is looking at this, and one of the important things is that Einstein then begins to look at light, photons, as having a certain particulate characteristic. And this, of course, is the famous photoelectric effect, where even if you increase the intensity of the beam shot at a foil of some kind or other, you don't increase the number of electrons that are bumped off. You might increase their energy, but you don't increase the number, because they come in packets. They only come at a certain rate. They don't come in as a continuous increase. So you're getting, you're getting certain kinds of phenomena that are completely different. Now, what's the relevance? Remember what Lynn was talking about. Also, of course, you get special relativity. People should begin. We'll come back on some of these things, but in particular, even though this seems maybe to some people, I wonder if I had that thing, the photoelectric effect, backwards. I often do that. But anyway, the special relativity. Okay, what's the point? It's not relativity in the way we think. It's not subjective relativism. It's not ethical relativism. It's not even the relativism of what Russell tries to turn it into. Since we have no fixed absolute time, it's all everybody's viewpoint on time. You have your viewpoint on time because of where you are. Richard has his view of time because of where he is, and there's slight differences. And somehow this is the importance of what Einstein does. That's not the importance of what Einstein does. It's not only not, it's the opposite in the following sense. What Einstein says is, actually, he's dealing with a different kind of problem. Classical physics is beginning to break down. It has, first of all, some of this character, but in particular, we have phenomena like the Michelson-Morley experiment. And there were others. It's unclear whether Einstein, how much he knew about that experiment. But there are problems that come up in electromagnetic theory. For example, in Maxwell's equations, the point, so to speak, that represents the charge, like you have a positive charge, a negative charge, or a moving elements, shouldn't really exist. It's an infinitesimally small point. Because a positive charge, what's the character of an object with a positive charge? Two things with positive charges repel. Now, if you stuff a positive charge, but it's still not zero, there should be a certain amount of, repulsion. It's the same thing that goes on with the nucleus of an atom. How does it hold together? Because if it's all protons, and there's nothing else in there in between, they should blow apart. Why don't they? Or you take the Michelson-Morley experiment, which more people are aware of. If you take a light ray and shoot it south, and actually they had to do that, and then you have a light ray perpendicular to it, and you set up a certain interference test, you should get a certain amount of interference, because think of it as going upstream in the river. Okay, so the person going across is going to end up going a longer distance because he's fighting the current as opposed to the person going with the current. Okay? So you should get a difference. You should get an interference pattern if you set up the experiment right. But what happened was, of course, there was no interference pattern. That means maybe the stream doesn't exist, or there's something otherwise peculiar about what's going on, but it certainly doesn't fit the classic picture of an empty box and some medium through which these waves are propagating, and you're dealing with, we're dealing with waves of that type. Now, what Einstein does is he says, well, let's look at this entirely differently. Let's leave this medium out. Let's drop the idea of an absolute space-time framework. What would the laws of the universe look like if they had to be true no matter where you were in the universe? From any perspective, you're going to try to find the principles that are the same for everybody. In other words, they have to be universal laws. What good is a law of physics if it isn't universal? If it doesn't apply to everything? It's not really a law of physics. Now, in a certain sense, keep that in the back of your mind, because at a certain point in the course of some of these discussions, we'll get to the idea that maybe there's something that even supersedes that. But for the moment, in terms of understanding what Einstein was trying to do, he was saying, look, these laws are falling apart. We're finding that the laws of electromagnetic propagation don't apply under certain circumstances. We're finding out other things of that nature. We've also got these peculiarities of the quantum phenomena. What physical laws would apply universally, invariant, as we used to, he called it? And that's what special relativity gives you. It's not that everybody's time is a law, everybody's perspective. No, in fact, everybody's perspective has to be subsumed under some guiding principle, some law. Now, of course, this led to some very interesting differences. The biggest difference, probably the most famous, but it is of a significant relevance, is the fact that under these conditions, and if you go through some of the experiments, you find that a certain amount of energy, or mass rather, is converted into energy. That in the course of motion, making all of these different perspectives have the same force laws, you find that a certain amount of mass is turned into energy at a very high rate. Think about how we live with this, but think about how shocking this is now. I mean, consider the fact that every little atom, which was being conceived of as just a thing, a rock, think of it as an object that's almost invisible. Yet, in the course of speeding that up, so to speak, accelerating it, a certain amount of that mass turns into energy. Or, for example, if you split a uranium atom, in the course of doing that, you end up with a slightly less mass than you started with. But that mass is multiplied by the speed of light squared. And how do you pack that much energy into that volume? I mean, even if you think about an atomic bomb, you're unleashing hundreds of thousands, millions of tons of TNT from, relatively speaking, a few pounds of uranium or plutonium or some combination thereof. It is one way to get yourself beyond the visible. This is not going to cohere with any sensory experience. And I think what you begin to see is, in the case of Einstein, science itself is moving more and more into the unseen. You're not going to experience this in any direct way. I think this is a good way to look at some of what Lynn was saying last night. If you think of 4 generations, or what he called the super future, I like to think of this, I was saying, this is like over the horizon radar. Most people can, they'll live to see their children and their grandchildren reach at least young adulthood, at least today in, let's say, an advanced sector country. Most people who are grandparents live long enough to see their grandchild. Maybe they'll see a great-grandchild as an infant. But you know that you're not going to be around at the present conditions to see your great-great-great-grandchild. That's something that's beyond your experience, and probably even beyond, at some level, what you can imagine the world to be, except as a linear extension of what you know now. So you're thinking of, when you think of 4 generations, and by the way, one of the best examples of this was Ben Franklin, who actually did pose the question. He said, I'd like to come back 100 years from now. Maybe there's some way they can pickle me. He had a sense of humor. Stick me in a wine barrel with pickling juice, and I'll stay. They can wake me up 100 years from now. This had nothing to do with Ted Williams, but he was more joking than Ted Williams was joking. But anyway, this is the idea that a great deal of the world that we really live in is not what we experience with our sensory apparatus. In fact, to do it properly, you've got to give up the sensory apparatus. Now, what we have, and what we're dealing with then, if you go back to what Lynn said about the original triad, what he's talking about, and these 3 generate a great deal of everything that goes on afterwards. You have Kepler, Kusa, and Brunelleschi. Okay, now what are you dealing with? Brunelleschi brings, and this is one, Lynn says the infinitesimal. Brunelleschi brings into actual practice, knowably, what we later call transcendental functions. These are functions that you can't express with a finite mathematical expression. In other words, you can't propose a formula that's got a finite number of variables, ax plus by plus cz, whatever it is, with 3 coefficients, or 4 coefficients, or 5 coefficients. No number of coefficients, no number of variables is going to be enough. You have to have an infinite series, which brings in a whole bunch of serious questions. I mean, because most people think of the infinite as a magnitude. It goes further and further and further. Well, that's a certain image of it. But the infinite is really not that. Okay? The infinite means beyond a certain boundary. You can get etymological, the non-finite. The finite means limit. And the infinite is that which isn't limited. It goes beyond the bounds. But the question then becomes, what are the boundaries? What the infinite really is the gap between one system, a way of measuring things, that has a limit. You reach a point where that measurement is not working anymore. It's not precise enough. It doesn't allow you to measure what you want to measure. You require an infinite series, which never bridges the gap. The only reason it bridges the gap is because you know that there's a limit towards which you're applying that infinite series. For example, in the calculus, one of the misdefined characteristics of the calculus, if you didn't have a limit point that you were using, you couldn't really properly apply the calculus. You would be identifying an infinite series with a hole that you never reach. That is a unity. What Leibniz does is he says, well, no, we're going to take a limit and we're going to create a concept of an infinitely small triangle that's moving toward that limit. And in the course of moving toward that limit, certain of the characteristics are going to drop out because they'll disappear, but some won't. And those will give you the measurement of the rate of change at that limit point. So this is what Brunelleschi brings into the physical world, because he uses this to solve the problem of constructing Brunelleschi's dome. Because the first application of this is the infamous case of the, you know what I'm talking about. What is it? Catenary. Okay? Because the catenary is constructed by the simultaneous application of a linear and a rotational action. And these are all the, when you peel the string off of a roll, the tractrix, evolutes and evolutes. They all have the same transcendental character. When you move from a linear action to a linear action and a rotational action together, you get a transcendental. You get something that you can only approximate by an infinite mathematical expression. Well, that's an interesting thing to realize. It means that the ontology, the existence that you're dealing with, is not replicated by the mathematics. The mathematics becomes a tool, a use of measurement. Now, the other thing that we're dealing with, of course, is Kusa. And I'll read you.
The ontology is not replicated.
It's not replicated in the mathematical expression.
Right.
Okay. You can say it's an infinite extension, but in a sense, it's meaningless. It means you just go on and on and on without knowing what it leads to. So what really makes it work is you know where you're going. So, Brunelleschi uses this to build the dome, which was considered, the greatest engineering feat of millennium. It was a scientific breakthrough, and this was the kind of thing that Kepler and then later Leibniz very much based their activity on. Kepler uses precisely this kind of conception. He's not worried about the mathematical expression. If it's an ellipse, it's an ellipse. And of course, what does he generally want to do? He says, well, let's take an infinite number of approximations of the ellipse. And he leaves behind the mathematical question, which is solved by Leibniz. So you can almost see Kepler and Leibniz as a one. Kepler opposes it because he says, look, in the world that we live in, there are variable forms of action that give us variable kinds of rotation. Ellipses, ovals, circles. We're not limited to circles. If you're dealing with only perfect circles, you can have one description, one transcendental concept, but that's all you need. What Kepler poses is we have a quality of ongoing change even in these otherwise accelerating actions, because properly understood, rotation is a form of acceleration. It's a change in direction. So it has to be handled from the same standpoint. Acceleration is not just how fast you can go in a straight line. Okay, acceleration includes change in direction. We're dealing with what are called vectors, which is a velocity or a magnitude and a direction. So if you're dealing with something that's constantly changing direction, even though it's not always changing velocity, you're dealing with an acceleration, a change. Now what Kepler recognizes is change is the character of the solar system. And what we have to look for, therefore, is some ordering principle, some harmonic ordering principle that's coherent with human knowledge, human development, human capabilities, in order to know what the solar system is like, which was effectively the universe at the time. So he does this by approximation. You may recall he does the area approximation and so on and so forth. He says at a certain point, I'm leaving this mathematical problem. So we're dealing with the human mind, the development of the human mind's knowledge, both the infinitesimal in Brunelleschi, the infinite or the universe in Kepler, and in Kusa, we're dealing with really the concept of the human mind, which Kepler brings together with the infinite and the infinitesimal to give us a conception of the solar system. Okay? Now, what are we dealing with now? The difference is there's nothing that represents quite yet what Kepler did for an advance in the situation. But Vernadsky poses the issue. Because Vernadsky wants to know what kind of universe gives us creativity or at least cognition. It's not 100% clear to me, if Vernadsky has the same sense of creativity, but he certainly has an idea of cognition, human intervention, scientific thought as a geological force. And he raises the question, interestingly enough, how is it that something like the mind can be an efficient physical cause? How can the mind determine the geology, the future of the planet? Or even more, it does go back to the old question, how is it that if you say I'm going to raise my hand, your hand goes up? But what allows you to do that? That's not as simple. It's not. Don't think that all of neuroscience has answered that question yet. They can give you a description of the neural networks and the whole 9 yards, but that merely your desire to move your arm moves your arm is a different kind of question. Now, what do we have? We have first of all, we're dealing with a whole new part of the universe. You have to recognize that until the end of the 19th century, based on the progress made in the nature of chemical elements, discovering what made up the elements, beginning to get an idea of what governs chemical reactions, physical chemistry, and so on. And also keep in mind the development of certain conservation principles. Because what happens with the conservation laws is that they're not conserved. We have the conservation of mass, we have the conservation of energy, we have the conservation of mass energy, and what we keep finding is that the form that we discuss it really doesn't conserve. Something else is going on. Matter is not just matter. Energy is not just energy. Even mass energy combined is clearly something that we're going to go beyond at some point. Because there are other forms of things that are supposed to be conserved, and they're not conserved. What we're going to get to at a certain point, just briefly in the discussion, is this question of symmetry and asymmetry is all over the place. The question is, where are the important, and how does the symmetry and asymmetry actually work? Just to give you an example, because people have heard, us talk about antimatter. What most scientists mean by symmetry is not what we think. Not that they're right, but it's just, in other words, we're thinking largely, I think, in spatial terms. Simple spatial terms. Something has a right-handed twist, a left-handed twist. Something's a little different if you move in one direction and move in the other direction. Now, there's nothing wrong with that. But what most scientists mean today when they talk about symmetry is that the laws of the universe are the same everywhere. Okay, so if you produce a positive charge, you produce a negative charge. These things, you don't have separate monopoles. You have dipole magnets, and so on and so forth. The universe is, from a standpoint of law, the same. Okay, asymmetries are when it seems as though there's a different law for some different kind of activity or different place. Now, this certainly does apply to these issues that were brought up by Pasteur. Why does life appear to choose a certain handedness when there's nothing in the what's ingested at all that's different. Why would we choose whatever it is, left-handed crystals as opposed to right-handed when there's no chemical difference between the two, no physical difference between the two? And that would be a violation. That would be asymmetry. Another good example of asymmetry is why is the universe made up of matter and there's very little antimatter? Just to have fun with the modern day physicists. They don't know. In other words, by the laws that they have, if those laws are equivalent everywhere in the universe, then you should have, by the laws that they're working with, you should have for the production of every positive charge or every piece of matter some example of antimatter where the charges are reversed. You have positrons and antiprotons and so on and so forth. Now, of course, the universe is made up of about 99.9% matter. Where did the antimatter go? That's an asymmetry. That's a big asymmetry. There are other things of that nature that are significant, because in fact, what is Vernadsky and what is Lin basically saying about the universe? If the universe produced human beings, and if human beings have the ability through their mental activity to replicate and discover and act on the principles of the universe, then in a sense, what is the universe that makes it accessible to human creative progress? Because our progress is not somehow mining the universe. We're acting on the universe and producing action in the universe, like using coal or oil or uranium. We're learning the principles by which you can make those resources act a certain way. Now, how is the universe constructed that it creates a mind of that capability? Now, the human existence is fundamentally asymmetric. In other words, we're future-oriented. There's a time direction, which means that entropy is not the law of the universe. Entropy is a time direction, but it's a reversal of in other words, the more you have entropy, the less able you are to develop. Human development is of the type that the more you develop, the more able you are to discover more about the universe. So it has an asymmetry in time of that sort. In fact, time in effect speeds up as opposed to slowing down. So the universe human existence is not entropic. And it gives you a clue that, and this is Lin's physical economy. This is why I think one of the I don't know what Lin thinks, but I still think to this day that Lin's physical economy, what it means epistemologically and ontologically, is underrated. It's as though you could skip now knowing the economics and how it developed and just get to the other ideas. Creativity. I'm not knocking it, but I'm saying I don't think you can quite skip what Lin did in the physical economy, because in there lies his fundamental discovery, which is what we focused on in the Hamiltonian economics. Hamilton's economic principle is the development of the powers of human labor. It's not commodities, it's not manufacturing simply. It's that the human labor power, i.e. the human mind, develops, changes, progresses, changes its relationship to the universe, changes in some ways what human beings are, like everything else. We're constantly developing, yet there's something that remains the same. Well, what remains the same? The power of development. And that's what we're talking about. So what we have, as we move into the end of the 19th century, we're expanding our reach into the infinitely small. And of course, at the same time, we're defining a different relationship to the infinitely large, which is then expressed even more in general relativity. Because now we've got a way of dealing with the fact that indeed the universe is not an empty box. Even in special relativity, you can live with that a little bit. With general relativity, you can't think of a box. Somehow, the very universe that we live in transforms. The universe is its own medium. And we have to define the nature of action and the relationship between actions in that universe. And there is a hell of a lot. Anybody who thinks, we're finished, forget it. Now all I want to do is read a couple things from Hilbert, and maybe we'll have a few minutes for questions, and then we got to shut it down. But yeah, I also just wanted to give you some sense of this triad. A lot more could be said. But now, in a sense, the problem today is to take Vernadsky's insight that you have to start, as Lynn does, from cognition and life, and then reflect back on what that imposes on the abiotic to define the necessary experiments. And I think we can get to the point of experiments, both in the abiotic, the biotic, and so forth, that we can do better than these other projects and determine experiments in space exploration, in biology, and so forth, that would give us a greater insight into what these asymmetries that lead to development, because it's not just asymmetry, it's an asymmetry that creates an asymmetry. And that second asymmetry is reflected in some expansion of human power. Now, I'll give you an idea of what Hilbert thought he was doing. Okay. It remains, okay. Okay, it seems to me that the numerous and surprising analogies and that apparently pre-established harmony, which the mathematician so often perceives in the questions, methods, and ideas of the various branches of his science, have their origin in this ever-recurring interplay between thought and experience. It remains to discuss briefly what general requirements may be justly laid down for the solution of a mathematical problem. I should say first of all this, that it shall be possible to establish the correctness of the solution by means of a finite number of steps based upon a finite number of hypotheses which are implied in the statement of the problem and which must be exactly formulated. This requirement of logical deduction by means of a finite number of processes is simply the requirement of rigor in reasoning. Indeed, the requirement of rigor, which has become a byword in mathematics, corresponds to a universal philosophical necessity of understanding. Okay, now, while insisting on rigor in the proof as a requirement for a perfect solution of a problem, I should like, on the other hand, to oppose the opinion that the only concepts of analysis, or even those of arithmetic alone, are susceptible of a fully rigorous treatment. This opinion, occasionally advocated by eminent men, I consider entirely erroneous. Such a one-sided interpretation of the requirement of rigor would soon lead to ignoring of all concepts arising from geometry, mechanics, and physics. Basically, to get an idea of what he's saying, no, this applies to everything. It doesn't just apply to mathematics or logic or whatever. So there's things I have to... Now, here's problem number 2. To investigate the consistency of the arithmetic axioms. Now, this is basically for a logical proof of the consistency of whatever formal system gives you the arithmetic. Number 6, and perhaps this is the one, to axiomatize those physical sciences in which mathematics plays an important role. Now in other places he says physics and chemistry and so on and so forth. And you begin to see where the reductionism of today takes hold. It's not as though reductionism didn't exist before, but it takes hold. This is why I keep saying, what happens here is this is the standard of truth. You meet this standard, a logical proof, a logical deduction. Nothing else that you do is true. Nothing else that you do is knowably true. You might accidentally, bump into something. And of course, this is exactly what's said about classical composition. You might do something that's beautiful, but there's no principle that guides that beauty. You do it by feeling, by accident, and maybe people have their differences. That's the area of there's only one area of knowledge, and that knowledge is 100% certain. Now, people can say, think about how much that rules, despite people's respect of their own opinion. What will they accept as truth? Very little. Or they'll accept what they can get from their minister. The minister says, here's what the Bible says, here's what it means, and here's what you can deduce from it. Okay, that's true. It says in the Bible that Samson, his strength was in his hair, he lost his hair, he lost his strength. Okay. And you say it's immoral to have children starving in Africa. Depends on how you feel.
It's not in the Bible.
It's not in the Bible, right? It's not in the Constitution. All right, so there's more to be said about some of these things, but I just wanted to also give people this idea of the triads, at least give you a beginning idea. That this is not just some funny trick. The one thing I would say is it's even clearer when you add what Leibniz did in response to Kepler, and realize that the whole of modern mathematics, to the extent it has value, comes out of that. Even carrying through to Gauss. Remember, one of Gauss's initial, even the fundamental theorem basically is based on the idea of algebra, is based on the idea that the algebra can be understood from the standpoint of geometry, from the standpoint of construction. That what you learn is the general principle that the number of times that the pathway cuts across a certain part of the space is determined by the power of the algebraic expression. If it's squared, it has 2 cuts. If it's a fifth power, it has 5 cuts. But even more, you realize that the series project is a great deal of what generates the rest of Gauss's interests, the anti-Euclidean geometry, and what even become, in the case of the series, an extension of the calculus into a so-called tensors and so on and so forth. So it's these are mystical names. But basically, a tensor is a complicated Pythagorean. It's not a whole lot different than what Pythagoras did for 2 space or 3 space. Now you're extending it into a number of different spatial characteristics. Or not space really, but different dimensions of action. So it's a complicated Pythagorean. And I don't even want, it's a complicated version of a squared plus b squared equals c squared. That's what Gauss's paper on the intrinsic curvature of surfaces is, the same principle. So what Kepler does sets the basis. And then you have what Gauss and in particular Riemann. And of course one of the things that Riemann says is the whole point is to go into the infinitesimal, into the astrophysical. Why? Because you need that to have the universe. And by the way, a lot of people are taught, relativity doesn't apply to quantum. It's not so simple, because you use relativistic principles in quantum mechanics. If you didn't have that, you couldn't have most of the experiments. Just to give you one idea, in most of these super duper collisions, if you just took a linear idea of the life of one of these particles when they are souped up into near the speed of light, their lifespan is 1 gazillionth of a second. Now you'd never be able to measure this because it would only be a little in your instruments. Why can you measure it? Because under relativistic conditions, at 99% the speed of light, you have time dilation. So the particle, even though it only lasts in its own terms a gazillionth of a second, from our standpoint, it lasts a few nanoseconds, and you can get a path. If it wasn't for that, boom, you couldn't. The whole thing wouldn't work. Or you'd certainly need much better instrumentation.
I just had a question about, you talked a moment about bacteria and viruses.
Yeah.
And one thing that struck me in looking at radiation is that uranium, polonium, radium, all these things, they possess energy. They're actually churning out energy. So, it's sort of like, are they alive or aren't they,
Well, I think they're
like
probably
a
not alive,
virus
but
problem?
but there's something clearly going on
Right.
that is not so simple in the non-living. That's really, to me, even more important. Because our conception of the non-living is wrong. There are certain kinds of actions in the non-living that, under the conditions of the laws of the universe, can be absorbed into the living. Without that, we couldn't function.
It's like cancer treatments.
Isotopes that the body deals with differently, and all kinds of other things in life that really don't function the way they function in the abiotic. We can reduce it to that for certain circumstances, but living conditions are a lot more complicated. So you don't get a simple linear do this and the body does that. Biology doesn't work that way. You can do that with some things. With non-living, you can say every time I move, the mechanical arm, it does certain things. It goes through a certain area. But you can't really do that with life. If you poke something that's alive, probably every time you poke it, it's going to do something different.
This idea that you mentioned, which is powerful, which is that when you get into Planck and Einstein, you did definitely have to leave the sensory behind as how you're knowing the universe. Could you say something about relating that to what Bohr and Heisenberg had to say in terms of what you can know, what's knowable,
Bohr and
what's not
Heisenberg
knowable?
both say explicitly that all you can really know is what your data is. And then you might have certain principles and certain mathematical descriptions of the data. You don't really, that doesn't tell you. Heisenberg and Bohr, even more than Bohr, but Bohr too, are explicit on this. You're getting a description that you can use to make predictions of what goes on in the atom or whatever, but that doesn't tell you anything about the causality or the real existence. And you really can't ask the question.
Right, well, that's
We're at
the key
the
part.
end. I mean, one thing that comes up is this whole idea of completeness. For example, Hilbert wants a consistent and complete system for mathematics, or at least for arithmetic to start with. He can't get that. There's almost no complete system unless you're dealing with something so limited in its reach that you can say it's complete. There's something called Sentential Calculus, where you're so limited in what you can express, you can say you can create a system that gives you all the truths. But even that's probably more striking about Gödel than the so-called proof of you can't prove the consistency. The real truth is, if you do prove the consistency, then it's not complete. So this is the real dilemma. You can get a consistent system, but it's too limited. If you try to get something that is more expansive, then it's not going to be consistent, or it doesn't have a simple consistency to it. So this is the reality of the situation. What Hilbert wants is something where you take the experiences, and in particular Heisenberg and in the debate, their point is all you have is the mathematical matrix. All you have is the wave equation, and that's a probabilistic wave. not a physical wave.
Yeah.
They use Schrodinger that way. Schrodinger wouldn't agree with it, but that's what it's come to mean. So the reality in this situation is you don't know what's causing it. You shouldn't even look for what's causing it. That was their argument against Einstein.
Yeah.
Einstein's argument wasn't that we know what's going on. Einstein's argument is we should look for what's going on. And their argument was no.
Right.
We've now reached, in fact, Heisenberg, I think it was at one point, said, this is a complete system. It's the end. It's like Fukuyama. It's the end of history. It's the end of science.
Well, this is very much connected to this question of what we were saying, this critical demarcation of 1900.
Yeah.
Because this attack on causation and knowability occurred
That's it.
at the same time.
And it occurs across a broad front. It occurs in music. It occurs, therefore, in all forms of classical composition. It occurs, and I think, Lynn was saying, there's no morality. In a certain sense, the 19th century had a morality of some kind in its direction. In the 20th century, you increasingly lose any sense that there's a moral direction in human history. You're just getting by, you're living, you're dying, you're trying to survive. It's ever more brutal. Now, I saw something today. I was like, and they've been doing studies on students coming into colleges, 18, 19, 20-year-olds. And the amount of pure anxiety, and well, the way they put it is, of course, interesting. The anxiety levels have now superseded the levels of depression as the standard problem of incoming students. Because so many of them are completely stressed by the demands on scores, holding jobs, and their parents are all over, and also social media. One thing that comes up in social media is you get people who, they're always putting out tweets about how, oh man, my life is so groovy, it's the greatest thing that ever happened. I just faked out 3 professors, I'm getting a degree, I got $1 million job. And so everybody else feels like they're idiots. I'm barely scraping along. I can't pay my rent. My mother thinks I'm failing. So the social pressure on these kids is beyond belief. And so the highest rates of medication, previous psychiatric sessions is characteristic more and more and more.
Why do you think this happened in 1900?
Well, I think
Some other time.
there's a simple answer. It's probably not completely correct. I think the fact of the matter is you have to look at the whole thing from the standpoint of, in many ways, you can say the Renaissance, but the American Revolution. I mean, there was clearly a determination to sustain the British Empire. See, all the other empires do collapse. The Russian Empire collapses, the Ottoman Empire collapses, the French Empire sort of attaches itself to the British Empire. The Austro-Hungarian Empire collapses. These are all gone by the end of World War I. There may be remnants, they may be tied into things, but they're gone. And it was clear to the Prince Albert VII, or whatever he was, it became Edward VII, that they needed to contain this phenomenon. Now we would say this Hamiltonian phenomenon, that science was progressing to the point that we could provide for effectively an ever-growing population and increasing standards of living. There was no limit to growth. And I think that they realized that they had to move in with a limit to growth. And I think if you look at Wells and Russell, you get a certain grip on it. I mean, this idea that Russell, who really is, it's not that Wells isn't bad. Wells figured the human character was such that you couldn't completely stop development. So you had to have some of your own development. And, secrecy and all this stuff. Russell thought science was an absolute evil and had to be destroyed. And it was the greatest danger on the planet was the human mind.
Wow.
And I think that's their lesson from the American Revolution and other similar things. Maybe it's not limited, from the Weimar classics, the development. You had a whole flourishing of the human mind. You could take different time spans, but certainly from the middle of the 18th to the end of the 19th century, it's an explosion.